sequences. So let's look at these two sets. I have two sequences written up here. One of them is 3, 6, 9, 12, 15. The other one is 3, 6, 9, 12, 15, dot, dot, dot. Exactly. So what happens here is that you have what are called finite and infinite sequences.
Or finite and infinite.
Now, what we do here is we talk about them as specific terms. First term of the sequence, second term of the sequence, third term of the sequence, and so on and so on. We look at it as these sequence values are actually values in the range. The domain of these would be first term, second term, third term, fourth term, fifth term. That's what that means. First term is 3, second term is 6, third term is 9, fourth term is 12, and so on.
That's the domain?
Yeah. The domain is which number is it in the sequence. The range is what it is. So these are called your
Oh, so like it would be 5, 15, 4, 12. Wait, just keep reading.
those would be the nth term of the sequence, like the fifth term is 15.
Yeah.
The
Okay.
sixth term would be 18. The seventh term would be 21, and so on. The value, that range value, is what we call the A sub n. So the fifth term in this case is 15. The third term is 9. Does that make sense?
Yeah.
So we use these little subscripts and things like that to know where certain values are within the sequence. Now, what's nice about this is that we can create and make what are called rules for the terms, and we can check these things through. We can, I'll get there. That's why I wanted to make sure you guys had calculators today, because I'm going to show you a way to always be able to validate what your guess is for a sequence and so on. Okay? What your equation might be, if you will. Okay? Not so bad?
Does it get worse?
It doesn't so much get worse. It gets a little bit more complicated, but it's not that it's going to be horrible. Today, I honestly think that today is the tougher of all the sections because there are no defined rules as far as what we're doing. So today is just like this real general stuff.
All right.
Tomorrow we'll talk about arithmetic sequences. Arithmetic sequences means you're adding or subtracting the same thing each time. And then on Wednesday we'll talk about what is called geometric. No, it's like triangle, triangle, square, triangle, triangle, square, triangle, triangle, square. What's next?
Triangle, square.
It's multiplying. It is multiplying. Thursday we talk about infinite sequences in series. Wait, infinite sequences in series? How can you count something that goes on forever? Hey, long time no see. Bad. Yeah. I thought it was good. All right. Okay. Do I ever need to ask you guys to write down the first 6 terms of a given sequence? No. You know why?
Because we're smart. SMRT.
Because it's busy work, but you also have a button on your calculator. For example, if we use this and go to the dun dun dun, y equals. If I go to the y equals table,
You can plug that in.
exactly. First term of the sequence is when n equals 1. Second term is when n equals 2, and so on and so forth. So if I type in -2 parentheses to the x minus 1, I can look at my table right away, and it'll tell me the values. The first 6 terms are right here. Okay? Now, the other reason why I wanted to show you that via the calculator is because when you come and start to write out your own rules for your terms in the sequence, the y equals table will help you to check to see if your guess is correct. All right? And that'll come into play here in a couple minutes. So don't worry, I probably won't ask you to write out the terms in a sequence because, like Hopworth said, it's busy work. Yes, sir?
I did not get that in my calculator.
Did you not close parentheses?
I did.
Did I not get that?
No, you're right.
Negative 2.
Just hit graph.
Oh, you're at 318, that's
Oh,
why.
what the heck?
So it's right now it's asking you to start your table at 318. Start it at 0. No problem. Anybody else? Table all out of whack? You guys know how to change your table set? Real quick. If you hit second window, it options you out to what's called table set. Connors had it set at X value of 318. So you can always adjust it. Usually, you have to start someplace else.
Then like something where it was like, what is it like for last week we did our calculators?
You might have done-
Like, that was
The last question was the last
Yes, ma'am.
Mr. Murphy,
Yes, ma'am.
so by plugging that in, what is the question actually?
That's actually what that is doing. Is it's taking the first 6 terms. Here is your n value, and this is,
Write them down.
and that's your a sub 1, a sub 2, a sub 3, a sub 4. That's all it would be.
Okay, so that would be a
Yeah.
Why would you always start at 1 though?
Usually the first term is 1, unless you define it to be something different. And I'll show you how that looks here. All right, this is where things get weird. I want to write the rule for the sequence. All right, I want to write the rule for these sequences. Now, there's a nice little kind of a trick to how I do these. Caught it. I wasn't even twirling it. So there's a nice trick that I do with these things in terms of domain and range. What I want you to think of here is the first term is negative 1/3. The second term is 1/9. The third term is negative 1/27. The fourth term is 1/81. What is the general rule for that? Yes, sir.
You multiply it by negative 1/3.
So you're taking your first term and multiplying it by a third?
Negative.
Negative 1/3. So what you're saying is your rule, your a sub n, which is your rule, is n times what?
Negative 1/3.
So it's negative 1/3 times n, is what you're saying.
Yes.
Okay, now, here's what I want you to do. Take this, put it in your calculator, and your y equals. One third. You said times n.
Yes.
Look at my table. Is that generating what I have there?
No.
No, it's not. What do you got? Now, when you put that in the calculator, what do you get?
So
Yeah.
times negative.
Now, what you did, and this is where playing around with the calculator is important. To understand what it's doing here. What it's doing is that you were saying is 1/3 times n, so it's 1/3 times 1, 1/3 times 2, 1/3 times 3. That's not going to work. Now, one of the things that you would notice is that, see how the signs are alternating between positives, negatives and positives, negatives and positives?
Yep.
In order to be able to do that, When you're multiplying things together, if you have even number of things being multiplied, it's always positive. If you have odd numbers being multiplied together, it's always negative. So this here kind of plays the idea that you have something to an exponent. And like Lou was just saying, what do you got?
Negative 1 over 3 to the
Negative 1 over 3 to
end.
the nth. So, oh, I see what you're saying. Okay, or you're saying negative 1 over 3 to the nth. Okay, that works. It works both ways.
How do you get it to flip that way?
On this one, this one will always stay negative. See, that's the problem with that one. Now, by going to this idea, when you start thinking about the rules of exponents, it's going to be negative 1 squared, negative 1 cubed, negative 1 to the 4th. That'll alternate your signs. Okay? Now, you start at 1, or what did you write down? You wrote x minus 1. Now, if you did negative 1 over 3 to the x minus 1, that means my first term would have an exponent of what? 0. What's anything to the 0 power? 1. This didn't start at 1, so this wouldn't work. I couldn't say it as at minus 1. But again, you could go back and forth, and you kind of saw it, but you didn't catch it where it equaled 1 to start with. See what I'm saying with that? So what happens here is you play around a little bit with the calculator to try and get you going. This table function is your best friend for a lot of these, because it's a lot of guess and check. Okay? Not terrible? Yes, ma'am.
So would it be negative 1
To the nth power. Yeah.
Okay.
That's all it is. So your rule would be a sub n is that. Okay? Now let's look at the other one. 2, 6, 12, 20. I'm going to write this on a separate sheet here. What I want you to think of again is if you look at it in terms of domain and range. These are my range. This is my first term, second term, third, fourth, and so on. One to get you 2, 2 to get you 6, 3 to get you 4, 4 to get you 20. Okay, you're right. 1 times 2, 3 times, or 2 times 3, 3 times 4, 4 times 5. What would the next one be?
5 times 6.
5 times 6 would be 30.
6 times 7 will be
42, okay. So what you're doing is you're taking 1 times 2 is 2. 2 times 3 is 6. 3 times 4 is 12. How do you write this in terms of n's?
N times 1? Or no, N plus 1. N plus 1. Oh,
N times n plus 1. N times n plus 1, where n is 1, 1 times 2, 2 times 3, 3 times 4. Yes, sir.
Would it be better to say n squared plus n?
You can if you want, but this is just as fine. Okay. This is just as fine.
So n is the domain.
Yeah. Well, n's not the domain.
Well, the value of the domain.
Yeah, the domain is term and sequence. So yeah, I guess I see what you're saying. So yes, n would be your domain because that is the value you're putting in for to generate your range. Okay. So your rule, your nth term is defined by that. And you're right. This section has a lot of these types of problems where it takes you a while to figure out what'll happen. But if you use your calculator, you guess and check a little bit, you'll figure it out. It's not too bad.
Is there any way we could get the wrong answer though and it still work?
Yes.
Oh.
There are many ways to write all this out. Well, I'll show you an example. I have one next of a way that I can write it multiple ways. Okay. So the difference between a sequence and a series is pretty simple. There's a plus sign. Series is what we call a summation. Series take all the values in a sequence and add them up. So what we use is called summation. It's called summation notation. So finite series is just taking a sequence and adding all the values, adding all the range up. So we use this. Sigma. Greek letter sigma. The Greek letter sigma in math stands for sum. And you liked it. And sum means addition. Now, when we write out these things, we have to figure out a sum value of some sequence. This sequence, 3, 6, 9, 12, 15, we had that one a minute ago. We wrote that as 3 times n. Remember that? So the rule goes here, 3 times n, where n is the number in the sequence. What value of n does that sequence start at? 1. So where n starts at 1, and how many terms are in the sequence? 1, little 2, little 3, little terms, 4, little 5. There are 5 terms in said sequence.
You know, Lofthouse was actually trying to teach me this at robotics, and it didn't make sense, but
It just adds up.
no, I'm just saying Lofthouse was like just writing stuff and it didn't make sense, but that makes sense now that you explain it.
Thank you. Now, what's nice about this is pretty easy. It's 3 plus 6 plus 9 plus 12 plus 15. It's probably quicker just to press those buttons in the calculator, but dun dun dun, there's a button for this.
Yay!
There's not for that.
Alpha zoom function. Oh, so it should be an alpha window. Alpha window 2. Alpha window number 2.
Wait, I'm confused on how you rate this.
Alpha window number 2.
I can see one.
So what you'll notice here is that you've got 4 spots that's asking you to fill in.
And I'm gonna guess that n becomes x.
Yeah, and the book uses n's, the book uses I. When you see I in this section, don't think of it as imaginary. We don't have any imaginary stuff here. It's not a big deal. They just, for some reason, decided to use the letter I. So I say my value of x, oops, and this sequence starts, or sorry, this series starts when x is at 1. First term, second term, and so on. You're going to define it. There's going to be made. X is the value in the sequence. How many? There are only 5 terms in the sequence. We're counting the first term in the sequence through the 5th term. Yes, ma'am. Yes. There are 5 terms, and then in the parentheses, you just put your rule, 3x.
Why does it say 45? Oh, is that because it's 50 plus 12 plus 9 plus 6 plus 3?
Yep. Yes.
So it's like a factorial, but more.
Yes. What's nice, and now this one obviously is really easy. You probably would have just added them all up by hand anyway, because it's quicker. But what happens sometimes is you're going to get one that will have 13 terms that you don't want to add together.
Oh, it's adding its friend.
Yeah. 3 plus 6 plus 9 plus 12 plus 15 is 45. That's what it's doing.
So let's say you wanted to start at 9, you just say like x is equal to 3. Because you want to start at the 3rd term.
Yeah. Yeah.
Yeah, wait, I know.
What's that? Guys, please.
What's the purpose of the series?
The purpose of the series is one of those things that, oh God, where's the example?
What does it find exactly?
When you're looking at consecutive rows of things, and we're going to get to like the fancy stuff of course in the end, it actually allows us to do some polynomial stuff.
Wow, we have to do that.
I don't think it's in this chapter. It'll be in the next chapter. We use this stuff with polynomials about exponent rules. you can do it with series, how things multiply out, the whole Fibonacci thing. Yes, ma'am. I can't hear you because everybody else is still talking. Guys.
Does the n equals 1 just mean that it's starting on the first term?
Yep, that's all it means. That's all it means. Okay. Now, the other one is a little bit different. Finite series has an ending point. Infinite series doesn't. I can't add this up. You know why? There's no button on the calculator that says infinity. There is nothing on the calculator that allows you to add to infinity. So, ladies and gentlemen, you cannot, guys, at least two of you will come up and ask me, where's the button for infinity? There is no button for infinity. You cannot add an infinite series together like this. We will look at infinite sequences Thursday. There is a special case for these things, but it's completely different. So there's no infinity button. Just want to get that out of the way here. There's no such thing as an infinity button. So let's write these in summation notation. Now, when it says write something in summation notation, you're going to write it out with that sigma symbol, but you also have to figure out the rule. And you have to figure out how many terms there will be within a sequence. So if I'm starting with 5, 10, 15, blah, 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 to 100, excuse me, you're saying the rule here is 5n. Everybody okay with that?
Why is it 5
5 times 1, 5 times 2, 5 times 3, 5, 10, 15. I have to sum them where n starts at 1. How many terms would be in this series then? 20 of them. Now this is a case that you don't want to add 5 plus, 10 plus, 15 plus, and so on and so on.
Unless you can do it in your house.
Can't. What are you going to say, Sadie? So you press buttons in your calculator, and you get what? You get 1050 when you do that. Now, a second ago, you guys were asking me, yes, it. I'll show you what you can define n to be something, whatever you want. And I was just about to show you an example. Now, there is a way that you could say, well, if n started at 0, how do I generate my first term? You add 5. So if I start, now say this is what you were asking a second ago, is there other ways to write this out? If I start at 0, 5 times 0 is 0, 0 plus 5 is 5. 5 times 1 is 5, 5 plus 5 is 10.
So you can make it unnecessarily complicated.
Correct.
I'm going to do that.
Could I have done this? Started it at 2 and done that. Okay, there are multiple ways to do this. And this is what people ask about. Is there one specific way? Normally, if you go for the real basic one, and that's when we're looking at,
Oh, yeah, I think so.
and that's what normally we would do. Okay? Does that make sense? So you can have multiple representations of series. It's very, very common. Very common. Okay? But more often than not, you guys will probably just write that. And you got, when you hit the buttons in the calculator, you guys are getting 1050? Okay. What about the other one? The next one's a little bit trickier. Put this on a separate sheet.
Oh, it's 1 over 2, 2 over 3, 3 over 4, 4 over 5. So, oh, I don't know how to write that in numbers.
So your first term, second term. Very good.
How did you know that?
And here's the trick for figuring that out. If you write down your domain value above it, first term is 1/2, second term is 2/3, third term is 3/4, and so on.
Oh,
You catch the correlation with the numbers. Yes, ma'am. This one is infinite. So I'm going to write this. I'm going to show you how to write this.
What's the rule?
We can write it. We can't calculate it, but we can write it. We okay if we start at 1?
Sure, why not?
Does this one stop?
No.
So it goes through infinity. Yeah. and that would be your rule. Okay? Big trick here for a lot of these things for you guys is if you write down what number in the series you're dealing with, first term, 1/2, second term, 2/3, third term, 3/4. A lot of times that's very, very helpful in determining the rule. Okay? Yes, ma'am?
So can you not solve that on the calculator?
I cannot, there is no infinity button on the calculator.
So no.
There will be a way of doing an infinite series, when it's an infinite geometric series. We can do that, and I'll explain that on Thursday. And it has nothing to do with an infinity button. There is no infinity button. Repeat after me. There is no infinity button.
Infinity button.
Sir.
Like this, there is no. Oh no.
Está allí. No está en mi clase.
So is it in Lobhouse's room?
Yes. Go over there and ask where the infinity button is. Sure.
Okay, let's go, Nick. Are you gonna lock us out?
Nope. I had it posted. The homework posted. Yeah. See ya. What would I do for this? I put it in the calculator. Do I need you guys to sit here and watch me press buttons to do that? They just change letters on you. You know, and I hate, they're going to write I. They're going to say I equals 3, 2.
Okay, but I.
Yes.
Really?
94.
Imaginary number.
Okay, you guys.
Which leads me to this.
Please.
There are special case rules for all of this, which means there's no reason whatsoever for you to memorize this, because who cares if this formula goes to this, when you can just put this in your calculator and go on your happy way. Bless you. Go for it. Yeah, I got one.
He says we need to get better calculators. And people.
Well, I have to use it in calculator.
And plus point yeah.
Yes, ma'am. What's up? I don't know. Figure it out. Figure it out. Play around with it.
We have been.
Keep trying. Give me a second. I'll put this up here for you too.
Someone told me we have a sequence quiz like later this week.
What's that?
Someone told me we have a test on this later this week.
Next week.
That was like,
No, next week. It's a short section, but not that short.
But it's on the day of.
There's some problems if you don't have them around the calculators or whatever.